My name is Zach Grinspan. I'm a pediatric epilepsy specialist at Weill Cornell Medicine, where I direct the pediatric epilepsy program there. And I'm here to talk to you all today about our trial using phenylbutyrate for two rare disorders, STXBP1 and SLC6A1. First, I just want to acknowledge this amazing team of physicians and scientists listed here who led to the study. Dr. Kang's work that she just talked about was fundamental to the idea of this trial, and so I'm indebted to her work as well. I'm also indebted to the funding. The study that I'm going to talk about was privately funded from a variety of organizations focused on treating rare diseases, including SLC6A1 Connect, so thank you for that. And then I also want to preface my talk with two things. One is to sort of, I'm very excited about the results of the trial that I want to share with you, but I want to temper that a little bit by reminding us that this is a first shot. It's an open label study. We in the epilepsy community, Scott Demarest has given me a thumbs up because we talked about this before. We've been burned before where we've gotten very excited about early results which then didn't pan out. And so I want to convey both tremendous excitement for this as a possibility, as well as caution that this is still very early, that this shows us that this is a promising idea, but we still have a lot of work to do to really flesh this out and know whether it's the right thing to do. The second thing I wanted to say is that, there's a lot of parents in the audience. I can't totally communicate how inspiring it is to have parents pushing this research forward. We were, Amber will remember, we had several phone calls as we were designing this trial, and there's nothing quite like having a parent on a lab meeting where you're like, well, should we do this, should we do that? And the parents are like, make a decision, move it forward, get it done. It lights a fire. It's really effective, and it's transforming how we do science in really important ways. And so, actually, I want to pause and just give a round of applause, to Amber and the organizers of the conference. This is how science is happening, so thank you. Okay, so two rare diseases, SLC6A1 neurodevelopmental disorder. Everyone here knows about this disease. Epilepsy is very common. Developmental delay and cognitive impairment are very common. Hypotonia, we heard a bunch about earlier today, is common. Many children have autistic spectrum disorder, movement disorders, problems with attention aggression, a high pain intolerance, sleep problems. And SLC6A1 is a GABA transporter protein, and so mutations in that lead to problem with these proteins. The other disorder that we studied is called STXBP1 Encephalopathy. Like SLC6A1, nearly all have epilepsy. Many of those children are refractory. The epilepsy continues despite medication. Intellectual disability is really the rule in that disorder, typically severe to profound. Autistic features are common, as are hypotonia, ataxia, tremor, spasticity, abnormal movements, etc. The brain MRI is sometimes normal, sometimes sort of abnormal in a non-specific way. And that's a gene that's involved in synaptic vessel trafficking, so it's involved in communication between cells, between neurons. So there were two remarkable bench neuroscience studies that led to our clinical trial. One was by Dr. Kang, showing that 4-phenylbutyrate rescues the SLC6A1 problems in the lab. And then at my place at Cornell, Jackie Bure was a bench neuroscientist, a PhD, and her lab had shown something similar with what she called in her paper Monk 18-1, but that's the same thing as STXBP1. So when we thought about doing a study, as the story goes, Dr. Bure, when she finishes her paper, knocks on my door and says, hey, listen, remember I was talking to you about STXBP1? I think we found a fix. And I said, that's amazing. Let's try this in people. What did you do? So what she said is she had done a couple of different molecules. One was called sorbitol, which is a sugar. and so I didn't know how to get that into the brain, because if you eat it, you digest it. Trehalose, another sugar, how are we going to get that into the brain? But the third thing that she had tried was phenylbutyrate, and we Googled it in my office. It's an FDA-approved drug for urea cycle disorders, and it crosses the blood-brain barrier. So we thought this was the molecule to try for a clinical trial. Phenylbutyrate comes in 2 different formulations. There's a sodium phenylbutyrate. It's quite bitter and salty and difficult to tolerate. And then there's a newer molecule called glycerol phenylbutyrate. They take this glycerol backbone and they glue these phenylbutyrate molecules to that backbone. So you take the liquid, which is the glycerol phenylbutyrate, and then you digest it, and the normal phenylbutyrates come out and do their work. I don't know why this drug is working. There's a bunch of ideas that are in the literature. We've heard from Dr. Kang some of her ideas, but there's actually a lot of different things that are out there. One idea is that maybe it helps with trafficking, i.e. as the cell is making proteins, maybe this molecule helps them get to where they're supposed to go. There's this idea of it working on aggregates, that sometimes you have misfolded proteins that clump, and those clumps can be toxic to the cells. So maybe it's helping protect the cell against those aggregates. There's this idea of endoplasmic reticulum stress, that the factory inside the cells that make proteins get stressed out when you have mutant proteins or when you don't have enough of certain proteins, and that maybe this drug helps protect against that. And then there's this idea of a histone deacetylase inhibitor, which is essentially about how the big DNA molecules, the chromosomes, fold and unfold, and that maybe by modulating that somehow you're leading to beneficial effects. The drug phenylbutyrate has been effective in other disorders. Back in 1980, they published an idea that for people who have something called urea cycle disorders, where you can't clear ammonia from the blood, that phenylbutyrate gives you a sort of a backdoor, a sideways mechanism to get rid of the extra ammonia in your blood. People have tried it for other disorders. They tried it for cystic fibrosis and had a little bit of effect. They tried it for a disease called spinal muscular atrophy. It did not work in that disorder. More recently, they tried it in Lou Gehrig's disease, in amyotrophic lateral sclerosis. They used it in combination with TUDCA, which is this bile acid, and they showed that phenylbutyrate in this combination form slowed progression of ALS. It didn't cure it, but it slowed progression. So we launched a clinical trial. We took all this information. We said, all right, let's give it to some people, and we decided to enroll 10 children with STXBP1 and 10 with SLC6A1. These were the inclusion and exclusion criteria. With STXBP1, we required seizures because it's such a prominent piece of that disorder. With SLC6A1, and again, power of parents on the call, as we talked to Amber to really understand the disorder, we decided not to have seizures as a criteria for entry for SLC6A1. And there were a few other exclusion criteria that in practice have not been a problem. There are known side effects of this drug because it's FDA approved, and we have seen some of them. The main ones, and you heard these from Whitney: decreased appetite, there's a sweet body odor, and sleepiness. We've seen those side effects. There's also an acidosis that can make the blood a little bit more acidic, and that's been another problem that we've had. When we did the study, we had a variety of exploratory outcomes that we were also interested in, which are listed here. So the study design, and there were many people here who were in the trial, and so this will feel very close to home for you. We did 4 weeks of phone calls, which is sort of baseline. How are you? What are your child's symptoms? How often are they having seizures? And then people came either to New York or to Colorado Children's for the first admission. This is supposed to have both of our sites there. Sorry about that, Scott. They were here for a 48-hour admission, and then we started the drug there at a low dose, and then folks went home, were home for 6 weeks, and then came back to New York for a second EEG that was one night. We initially thought, like, that'll be it. We'll just, we'll taper it off, and then we'll report out. Our first patient, which was a child with STXBP1 who was regularly having seizures 3, 4, or 5 times a week, went 20 days without a seizure after starting the drug. And so we called the company. We said, we don't think we can stop the drug now that it might be working. And so they allowed us to have something that we called extended use. And so now for the children in the study, we did this core 14 weeks, and then the majority of those children are continuing the drug to see how it does for the longer term. So here are our early results for seizures. This is all 20 children who we enrolled. The green are the responders. The yellow we called indeterminate, and I'll explain that in a second. The red are the non-responders, and then particularly in SLC 6A1, there were 4 children who did not have seizures, and so I'm listing them here for the sake of completeness. So a few words about this slide, and then I'll focus in on the SLC 6A1s. There were several children, 3, who got better. The seizures were a little bit less. But we weren't convinced that it was us, that it was from the trial drug, or that the improvement was minimal, not that much. And so we wanted to give them, we sort of didn't know what to do with them, so we called them indeterminate. And then in the STXBP1 population, there were 2 children who had this quite severe form of epilepsy called epileptic spasms, who really did not respond. We gave them the full dose, there was no change. And so those are they in red. I pulled out just the SLC 6A1 so we can look at them together. Of the 6 children with seizures, all responded. And response here was 50% or more reduction in seizures when we measured it at 10 weeks. A few words about this. The seizure type in general that we were measuring, we're not exactly sure what they are. In some children, it's very clear. They're absent seizures. We have this classic EEG pattern, spike wave, they stare, and it matches up. There are other children where there are blinking spells, the EEG sometimes changes, and it's a little bit harder to tell. The other challenge with absent seizures, as the seizure type that you're measuring, is they're really hard to count. So as we think about what we've learned from this study for other studies of other drugs in SLC 6A1, having a seizure outcome is important, but it's not clear that you're going to be able to say, that this child went from 37 to 22 because absent seizures, they happen so often, they're often uncountable. This is not an unsolvable problem. It's just something for us to keep in mind. But what you do see is that more than 90% in 4. One child did not have any more seizures after starting the drug, and then there's one with 50% reduction. You can see the seizure types are largely absences or blinking and staring spells, but one child had a more severe set of seizures with atonic seizures and generalized tonic-clonic seizures. I have some early information about non-seizure outcomes. I would take this with a real grain of salt. I'm showing it to you more to give you a sense of what else we're measuring We're looking at communication through a measure called the ORCA. We've crunched the numbers on 11 children in the trial, and 8 of them improved. We're looking at sleep through something called the CSHQ, and of 12 children where we have those numbers, 5 improved. We have a quality of life measure, the PEATS-QL, and a few improved there. These we're still working out. We want to correlate them to see if this correlates with drug response, if this is independent. And again, knowing that phenylbutyrate is one of several therapies that we hope are in the pipeline, we want to be able to communicate what we've learned from our trial so that other people doing trials can learn. This, I've said this a couple times, this is maybe one of the most exciting 2 slides that I've ever put together. This is, and as the chief scientist of the study, I can't tell names and I can't tell stories. But there was a 5-year-old boy with SLC6A1. This was his initial EEG. This was a brief absence seizure. This family was quite good about pressing the button, and so we were able to do the correlation. Brief staring spell, brief inattentive spell. And for those of you who are used to looking at EEG, you can see this high amplitude delta pattern with these notches in it. So it's sort of a spike wave. There's an Angelman's-like quality to this. In other talks, you've heard about this delta. Dr. Goodspeed talked about this periodic slowing. Many children with SLC6A1 have similar bursts that are like this, but not quite so sharp. They're a little bit softer and rounder. And so as an epileptologist, when you've got the little sharp pieces, you're like, oh, that's epilepsy. But if it's just rounded, we tend to use softer language, delta slowing, cerebral dysfunction, which are these vague terms that aren't, the FDA is not going to be that interested in them. In the terms, the measure they're going to be interested in, that I wanted to qualify that. And I'll show that in a second. So one of the nice things about EEG is that it's data, so you can crunch it and you can do all sorts of fun things with it. This is one of the tools that we use just in clinical care. Will give us something called a compressed spectral array. If there's any electrical engineers in the audience, it's a spectrogram where you see power versus time versus frequency. I don't know how well it shows up. It's on my poster also. But this child, each of these little vertical spicules in this compressed spectral array is a seizure. You can see there's maybe 30 of them, and this is 1 hour of data. So this child was having 30 of these an hour. And then when the child came back 6 weeks later, the EEG was essentially normal. Those spikes had disappeared, the spike waves had disappeared, the absence seizures had disappeared. This child is the respondingest responder in our study. This was the best outcome we've seen. It gives us hope, obviously, and it's tremendously exciting. It makes a really nice slide at a presentation. But what we don't know is how generalizable this is. We're still trying to figure out, is this something that we can do for everybody? Is this something that's just based on the mutation, on the age? Is there something specific about this? And we're still learning. But that said, this was, I was on rounds. Amber, I told you this story. I was on rounds, and I had 2 children in the study, both of whom responded. And I stopped with the residents. I'm like, we just have to pause. This is the best day of my career. right now, we did a trial. It's working. So, when you have those wins, you have to celebrate. Okay, so, and then qualitatively, we haven't had any new adverse events. It's an FDA-approved drug, so they already know what the list of adverse events are. And as long as what we saw was not different than that list, we could check the box that we were being safe. And so that box is checked. The odor, the sleepiness, the appetite suppression we saw, the metabolic acidosis we knew about, and one child did have that and withdrew from the study. Tolerability is, we really have not heard any problems with missing doses. It seems to work for tonics and absence seizures. For those children with STXBP1 who have epileptic spasms, this drug did not work. And then we're hearing narrative about increased engagement, increased alertment, improvement in language, and things like that. We haven't measured that yet, and we need to, but right now we don't know whether those anecdotes are going to be measurable. And then the limitations, as I said, open label study, the absence staring spells. Are they seizures? Are they not seizures? What are they? And counting them is a challenge. And then next steps, we're still running the full analysis. Phenylbutyrate cost $800,000 a year and is still the glycerol phenylbutyrate. Horizon Therapeutics has very, very generously provided it to us for the study, but just for those 20 kids. So we want to do more studies, but we're still working on sourcing phenylbutyrate for those studies. It worked for 2 disorders. Why not others? So we're thinking very actively about other genetic causes of epilepsy, monogenetic causes of epilepsy, SYNGAP1 in particular, and then there's some bench data on a creatine disorder, creatine transporter disorder called SLC6A1. These EEG changes, in collaboration with UT Southwestern, we're really excited about figuring out how to quantify those so that we can make it as an outcome, and then we'd love to do a definitive trial. What's interesting about a repurposed drug is that the definitive trial is not really for the FDA. If we're making a new drug, it is. But if for a repurposed, it's not really for the FDA, it's for the insurance companies. And so the bar is just different. We need to publish papers that are sufficiently compelling to get somebody to pay for it. We already know that it's safe. We already know it's okay to give to humans. So as this comes together, as we get all the data crunched, we will be publishing the results, and I'm always happy to talk about this with folks and let people know how about our progress. Thank you.